welcome. I see that my first talk was not so bad that all of you left, so that is, you came back for more. That's good. That's always good to see. I was going to talk about adventures in a legacy code base, but I failed to get my slides done, so I thought instead we would just look at some vacation photos that I've taken here in Italy over the last week that I've been, touring around. So I started in Florence, and they've got this nice big church there, and it's a beautiful city, Florence. It's very nice. I enjoyed that very much. Okay, I'm just kidding. Thank you. Yeah. That was the shortest and best talk I've ever given. All right. So, adventures in a legacy code base. So Raphael and Marco invited me here to give two talks, and I suggested one of them should be on coroutines because it's the awesome new thing that we are really excited to be getting into C++ soon, we hope. And Raphael suggested that the second one should be a talk about the project that I've been working on at Microsoft for the last 3.5 years or so. And so we've recently finished that project for some definition of finished. So I'm just... I've talked a bit at a few conferences about legacy code and tried to give advice on things that people could do to improve legacy code or best practices for writing modern C++. But today I'm not going to do those things. I'm actually just going to talk about our experiences in dealing with a large legacy code base, trying to modernize it, bring it up to speed, and hopefully people can learn from our experience from having done that. So the project in question is called the Universal CRT. And the project started off as what was called the CRT refactoring and unification effort. So for those who don't know, the CRT is an acronym for the C runtime, and it's Microsoft's library that is both the C standard library implementation and has a bunch of runtime support functionality that is needed in order for your program to run. So for example, it has the actual entry point for your executable that goes and initializes all the global variables and sets up all the standard streams before calling your main function. It also has things like the C++ exception handling implementation, the runtime type information or RTTI implementation. So it has a whole bunch of support functionality that's needed for your code. The project had two parts, as the name implied, refactoring and unification. We're going to look at the unification first, which is the goals of the project, what we were trying to achieve, and then we'll look at some of the things that we did in the refactoring that allowed us to achieve those goals, or we hope will allow us to achieve the long-term goals. This is not the story of how we wrote some awesome, amazing, terrific new C++ from scratch. This is about how we took some ugly and very old C++ and made gradual improvements to make it not perfect, but better. I also just want to note, I don't mean this talk in any way as any kind of advertisement for Microsoft's platforms. I'm purely interested in the technical side of this, just what we did. So, how things should look. So, at the very bottom on the Windows platform, we have the Windows operating system. And it's what we call a stable thing, right? If you call the create process API to create a process and you write your program today, you expect that in 10 years your program is still going to run on whatever the latest Windows is in 10 years. This has generally been the case. Software that is 20 years old is still running generally on Windows. There are exceptions, but for the most part, we have a very strong application compatibility requirement that we maintain compatibility with especially large and popular applications, but we try it for basically everything. So then, on top of Windows, because you don't want to write, just Windows system calls, that A, would be very tedious for many things, and B, you would not be able to port those programs easily to other operating systems. And so we have some libraries that we provide that build on top of the Windows API. And the base layer of those libraries is the C runtime. So again, this has the C standard library, so fopen and printf and things like that. And then on top of that, we build some C++ libraries. So these are the main ones that our team is responsible for, the C++ standard library, so everything that std string and std the IOStreams library, things like that. MFC is, of course, the Microsoft Foundation classes, which is started off as a UI framework more than 20 years ago and is still widely used by a lot of applications. Concert is a concurrency runtime, etc. But the key point here is that they all sit on top of the C runtime. And then you build your apps and libraries and other things, and you use these libraries, and you use the Windows platform. And just in order to keep the slides a little simpler, I'm just going to lump those C++ libraries into one box. So this is how things should look. But that's not how things actually work today. So this is how things worked through Visual C++ 6.0, which was released in 1997 or 1998. But we had this problem that as we kept making improvements, and we were making rapid improvements at that point in time, because that was a long time ago when we were still implementing a lot of these things brand new, we'd make changes to the C runtime or the C++ libraries, and we'd ship them, and we would break existing apps. Right, so everyone was using the same C runtime, and we'd go and make a small change to the behavior of some function. Maybe it was to make us conform better to the C standard, and now now that function behaved in a way the application that already exists wasn't expecting, and now it stopped working. And so we got a lot of flack over time from that. Basically, we were breaking our application compatibility guarantee that we were trying to make. And so what we started doing with the next release of Visual C++, VC7 or VisualStudio.net, Raphael has a t-shirt on from that era, we started basically releasing whole brand new sets of libraries with each release. So what ended up happening is we still had this stable Windows platform. So again, you call create process, you call create file. Those are still going to work the same way they do whichever release of Windows you're using. But in Visual Studio 2003, we released a 2003 version of the C runtime and libraries, and people built their apps and things on top of it. And then we released a new Visual Studio in 2005, so we had yet another CRT and set of libraries that we built. And we did it again in 2008, and again in 2010, and my slide isn't wide enough, otherwise you'd see we did it again in 2012 and 2013 as well. So the good thing about this was, basically, once we shipped one of these sets of libraries, we tended not to touch them again. So, we would ship the Visual Studio 2010 libraries, and we would go back and we would make critical security fixes if we needed to, or if there was some bug that was affecting a really important customer, or Windows or something like that, we would go back and we would make a targeted fix for that. We didn't do actual feature development or performance improvements to those libraries. We would instead take all those changes, those improvements, bug fixes that we were making, and we'd make them to the next version for people to be able to use. And by doing that, we ensured that we weren't going to break that backward compatibility guarantee which we had before. So the problem here is that this isn't even what the world really looks like. The problem is that the world tends to look more like this, where some library developers will go and they'll build, a library. And they'll build it against whatever the latest Visual Studio is of the day, or the particular Visual Studio that they tend to be using. And then you, or an app developer, will go out and build their app, and they'll want to use these libraries, right? You'll want to use, and we'll have an example of a specific library in a moment, but you'll want to use these libraries. So for example, if you're using your app and you're using library A, B, and C, and you yourself are trying to use Visual Studio 2010, you actually have a dependency on 4 completely different sets of libraries. So in theory, as long as these libraries completely encapsulate their dependencies, on these Visual C++ libraries, that's not a problem. That is designed to work that way today. DLLs are independent in memory. Really, the only cost that you have is that you end up loading all of these extra DLLs in your process, and so you use extra address space. Your installer is bigger because you have to install all of these things. But it turns out that in many cases, libraries are not that well self-contained, and they tend to leak out the fact that they depend on a particular version of the runtime libraries. And so for an example, we can consider an XML reading library, because XML is the latest and greatest of 1998. Maybe today it should be a JSON library or something similar. But we can imagine a library that has a function, read XML from file. And it takes a file star, so just a normal C file, and it returns you an XML document. So it'll probably call fread to go and read in the file, and then it'll parse the file and do whatever it needs to do. So let's say you've acquired this awesome XML parsing library in the form of awesomexml.dll, and the person who built it using Visual C++ 2008. So that DLL will have a dependency on the Visual C++ 2008 runtime libraries. So then you build your cool program, and since, we'll pretend this was last year before we released Visual C++ 2015, you want to use the latest and greatest, and so you build it using Visual C++ 2013, and so you end up with something that looks like this. And then in your program, you call fopen to go and open a file, right? So you call fopen, and you get a file from the Visual C++ 2013 runtime library, and it's going to hand you back a file star. And take that and be like, all right, I want to parse the XML from that file. So you pass it to read XML from file, which is implemented in awesomexml.dll. At this point, you're still okay. But then awesomexml.dll calls fread, and it's going to call fread from the Visual C++ 2008 runtime library. And at that point, it's not going to work. And the reason it's not going to work is because you've got a file, a stdio file from this CRT, and you're passing it to this one, and it's not going to know what to do with that. Specifically, there's some internal state that it maintains that relies on it being used only with the runtime library with which you opened the file. So this is a big problem, and this is a very small example. We have customers who run into this with very large applications or very large complex dependencies. As a specific example, Python has this problem today. So if you use the Python 2 line of Python releases, they depend on the Visual C++ 2008 runtime library. And I know that they've wanted to move forward to later versions of the compiler and toolset, but Python actually exposes some of the underlying POSIX APIs, like fopen and things like that, from the runtime library that it's built against. And since there are plugins that are distributed in a binary form, they can't change the library that they're depending on without breaking those plugins. So this is a problem that affects both library developers and app developers. So this is a fairly bad situation to be in today, both for library developers and app developers. So as an app developer, if you have source code for awesomexml.dll, you can rebuild it. It may take a little effort. You may have to tweak a few, places where conformance fixes in the compiler have, broken the code, or, that were non-conforming, or maybe you run into new compiler bugs that you have to work around. But in principle, if you have the source code, you can build it. If you don't have the source code, though, you're kind of in a bind. So certainly you can ask, whoever you got this DLL from, if they can build a new version of the library using the same version of the runtime that you want to use. But in many cases, perhaps they will charge you a large sum of money for doing that, or they won't be interested in doing that, or in the worst case, the company who built it is out of business and they can't, there's no one left to do that for you. You can try and write an abstraction layer over this DLL to bridge the gap. We know of people doing this. Or in the worst case, or at least from our perspective, the worst case, you can get stuck on Visual C++ 2008 for your own stuff. So you can get stuck using the particular version of the library because other things that you interact with use that version. And so that's the Python case. As a library developer, you also have a few options. So you can, re-release your library each time a new version of Visual C++ is released, or each time a customer asks you to do it. You can ignore the problem entirely and just force your customers to use the same version that you use. Or finally, you can design your library's API such that you can avoid the problem altogether. Now, this third option is actually the best option, and we highly recommend that option anyway. It helps, if you can encapsulate as many of your dependencies as possible, that's in general a good thing. But in practice, there are many libraries, especially libraries that were built for POSIX systems, that don't have this problem, where that kind of redesign would be extremely costly and not worth the effort. So if we look again at like how things should work, like we would really like them to work like this. And what we can see is really there's a red line here where everything below that line is what we would call stable. So, if you take a dependency on things below the red line, they'll continue to work. Over the long term, you're not going to have these sorts of compatibility issues. Things above the red line, though, if you take dependencies on those, you may be opening yourself up to the kinds of issues that we just discussed. So our goal with the Universal CRT project was to start raising that line. And so what we did was we actually raised the line. It took me so long to figure out how to do that little animation in PowerPoint. So we basically did the first raising of that line to make the C runtime piece of it be part of the stable platform that people can build on top of. Still, if you take dependencies on the C++ standard library or any of the other C++ libraries that sit on top of the C runtime, you're still going to be coupled to those. But our goal is to gradually ratchet up this line to increase the surface area of the platform that can be used, without running into those problems we had. So, the result of that was what we ended up calling the Universal CRT. I don't actually know how we ended up with the name Universal CRT, except that in Windows 10 we released the Universal App Platform, and I think that a program manager may have just decided that everything should be universal, because that was the new word, and so we ended up with that. But anyway, the important thing is this is the goal is that this will be the last version of the C runtime. So the DLL is actually named ucrtbase.dll. It doesn't have a number in it like all of the other versions of the C runtime that we've built. So future versions of Visual C++ will have this same CRT. So we just released version 14 last year. And when we release version 15 someday in the future, then things that you build using that version of Visual C++ will continue to use this one universal CRT. That doesn't mean we're going to stop work on it like we had in the past with older versions. It just means that we're going to be updating it in place over time instead of, by introducing new DLLs, side by side. There are a couple other points about it. So in addition to doing this, we actually moved the CRT into the operating system, so it's now a part of the Windows OS. A lot of Windows OS components now use it instead of the really old C runtime that the Windows operating system was previously using, which was similar to the Visual C++ 6 C runtime. And this solves the file star problem that we saw, but only for the future, right? Like if you have any existing libraries, we can't actually solve that problem. That is, like we've shipped the different versions of the DLLs, it is what it is. So our goal was, if we can't fix the past, then we're at least going to try and improve things for the future. There's a couple other benefits that we get from this. One of them, which I tell people about and they think is a small thing, but it's actually a fairly big thing, is reduced resource usage. So each C runtime is about a megabyte in size, and previously processes might load 5 or 6 in some cases of the C runtime, and so you end up with 5 or 6 copies of this thing loaded, which both takes up address space and it takes up, space in actual memory. People who carry the DLLs along, alongside their app, you've got disk space usage, and I look at it and I'm like, okay, 6 megabytes, that's not a whole lot, but the performance team in the operating system, 6 megabytes is a lot that they're excited about. And it's far easier for us to make bug fixes and improvements because now we're updating this thing in place, so that's the one thing that we're going to be updating. We don't need to worry about backporting fixes or things like that. But as I said before, we stopped doing this back in Visual C++ 6. We stopped updating in place because we weren't able to make changes without breaking compatibility. And so in the process of moving to this new universal CRT model, we also had to figure out how to basically restart that promise, basically start being able to make changes to the library and maintaining compatibility. So what do we really mean when we say compatibility? Well, there's 3 different layers that we consider of compatibility that we like to look at. So the first is binary compatibility, and this is if you build your program today, and you're using the libraries, then your program will continue to work 10 years from now, regardless of what changes we've made to the libraries and pushed out over Windows Update or Microsoft Update. This is the must-have, absolutely critical feature. If we break this, then the platform is of no use to anybody, because any Windows Update could break anything. Now, granted, sometimes that does happen, but they tend to be rare. A slightly lower level of compatibility is, or it's a higher level of compatibility, but less important, is object file compatibility. So this is, if you build a static library today and you link it into a DLL 10 years from now, it will still link and it will still work correctly. This is highly desirable because it allows people to distribute static libraries that people can consume. But on the Windows platform, static libraries are not our primary unit of code isolation. So while it's highly desirable, it's nowhere near as important as the the binary compatibility. And the third kind of compatibility is source compatibility. And this is fairly simple for the C library, which is basically that if you have source code that you built using the latest version of the C runtime SDK today, and you take that source code in 10 years and build it with the latest version of the C runtime SDK, then it will still compile. This is desirable. It's a nice to have, but if we make a few changes to the headers that may require you to make a few tweaks to your code, that's not terrible because you're rebuilding your code anyway, and so a few small changes. It's not the kind of issue that the app compat breaks are. So how did we get to the point where we thought we could guarantee this binary compatibility? And the answer to that was we did an enormous amount of refactoring to the C runtime codebase. So I guess just as a very brief introduction to the C runtime codebase, it is older than I am. I have, in the process of the refactoring, I broke tests that were written when I was 2 years old, and I edited files that are older than I am. So there's that. It's I actually don't know how big it is in terms of lines of code. For those who are interested, we ship most of the source code with the Visual C++ SDK. You can't build it, but you can. It's there for debugging purposes and reading. So most of the source code's there. So why did we need to refactor it all? Why couldn't we just take what we had in Visual C++ 2013, and declare that this is the stable thing? We're not going to make any breaking changes to it. One of the biggest reasons is we had substantial technical debt that needed to be addressed. So the code base was very old, and it had never really undergone a major refactoring in its entire lifetime. There had been basically patch upon patch upon patch have been applied, and as we'll see in some of the code examples, the cruft built up, if you will. We had some known C and C++ standards conformance issues. Generally, these were due to one of two things. Either we had bugs that had just never been fixed. Sometimes, we'd known about them for a long time, but fixing them was considered to be, too disruptive at the time. And now that we were making this big disruptive change anyway, this was a good time for us to make them. The other reason that those had come up was often due to divergence between what we had implemented and then what was later standardized, or what was implemented and standardized in parallel but differently. We had some APIs that were impossible to declare as being stable in their existing form. So for example, the C++ ABI on Windows, so name decoration and exception handling and things like that, is not well specified. So it's well specified within a version of the compiler, but as soon as you move to a new version of the compiler, all of that can change. In practice, things tend not to change, or at least they don't change very quickly. But there have been several major ABI, there have been several ABI breaks in the past. Whether or not they're major is another issue. And then there's some APIs that we had that expose internal implementation details. So it's just an example of some of the technical debt that we were looking at. So we have this function chsize. It's got an _s because it was, secure. Anyway, the specification of this function was that it would change a file size, assuming the file was open for writing, or we can't do it. And then it had a little example of how this function did it. We write null bytes because DOS won't do this for you if you lseek beyond EOF, but Xenix will. So this was in the Visual Studio 2013 source code. we have not supported DOS or Xenix for quite some time. I actually don't know what the behavior of Windows is. We've left this in its current state. But I laughed when I read this because neither of those OSs has been in widespread use for a long time. So we made some base improvements. Like these were the things that we started with, or that we tried to aim toward as we were refactoring. The first one was that we converted most of the CRT source files to C++. They were actually mostly C++ to begin with, even though they had .c file extensions. But we converted the rest of them to C++. This was generally painless. We had to add some casts in places where things were implicit in the C. But generally, this was fairly painless. And the reason we did that is because it enabled us to use a whole bunch of basically all the new awesome C++ features, like RAII, which is not remotely new, but to make the code simpler and easier to understand. We also fixed, we used to compile with warning level 3, and we bumped that up to warning level 4, and then started enabling a whole bunch of off-by-default warnings, basically just trying to smoke out bugs. And we fixed quite a few issues, some of which were real bugs that were identified by those warnings. We had something on the order of 5,500 if-defs and else and elifs and things like that in the source code when we started, and we removed something over 3,000 of them. So this, by itself, dramatically improved the readability of the code, because when you're in a function and you've got like 12 layers of nested if-defs and you're trying to figure out what's the next statement you're going to step to when you're debugging, it's not a lot of fun. For those of you who work on Windows, if you're familiar with tchar, it's either wchar or char, depending on the macros that are defined when you're compiling. We used to do C-style generic programming where in the CRT, where we would compile a file twice, once with Unicode defined, and so it would compile with wchar, and once without it defined, and so it would compile with char. And then we would have a whole bunch of if-defs in the file, and we'd use a bunch of macros in order to call the right different functions. So we ended up converting most of that C-style generic code to use very simple templates, which switching to C++ allowed us to do. This was just a little thing we did while we were working on it. We used to need something on the order of 900 MS Build projects just to build the 80 or so CRT libraries and DLLs that we ship, and we got rid of most of those and dramatically simplified it. And then we made some source code changes to substantially refactor and simplify the most convoluted parts of the library. So we used to have 4 separate copies of the startup code, and they had gradually diverged, to the point where there were bug fixes in one copy, and depending on which main function you use, you might get the bug fix or you might not. So we refactored those to try and get down to one implementation that had the correct behavior. And we did substantial rewriting of the I/O library because it both has the most complex code in it, beyond like the math library, which is a different type of complexity. So converting from C to modern C++, and I put modern in quotes because it's not really the modern C++ that we'd go to a conference and say, this is how you should be writing your C++. I just mean that it's far more modern than what we had before. So we kind of looked at it and we said, well, which language should we use when implementing the C standard library? And the obvious answer to us was, well, C++. And the reason is C++ has so many more features that you can use than C, and it makes writing simple, straightforward code so much simpler that it was just a no-brainer for us. Certainly, there's also some handwritten assembly, like the math library, for example. A lot of the really high-performance functions have very finely tuned assembly, but in something like the I/O library, you don't need to use assembly for that. It's C or C++ is going to be plenty fast. So this is what I was talking about, that there's C++ just has all those extra features that make it so much easier to write simple code, and we'll see in the next sections what those were specifically. I should note that we could not use all of C++. The biggest thing that we couldn't use was we could not take any dependencies on the exception handling runtime, because we have things that use the C runtime that expect that the exception handling runtime is not present in their binary when we statically link. And so because of that, we also couldn't use operator new and delete, and we couldn't use polymorphic classes, which are classes with virtual functions. We did not actually miss any of these things when doing this work. So before I look at some of the things we did in detail, the source code in these slides is based on the CRT source code. I often made some little renaming tweaks just to, we have a lot of extra annotations and things we have to do in the runtime source code, or we have to use ugly-looking names in order not to conflict with usernames. So it's based on the C runtime source code. It's all very similar in spirit, if not in fact. Like I said, all the source code is shipped as part of, in Visual Studio 2013, it's part of the Visual C++ SDK, and in Visual Studio 2015, which has the universal CRT, it's part of the Windows SDK. And so you're welcome to go and browse them and look at the differences between them if you're interested. And finally, I'm going to discuss some implementation details of the runtime library. That does not mean that you should go out and take dependencies on those. We can change implementation details at any time, and we often do. So the first big thing that we looked at doing was simplifying code using RAII. I know that this was talked about in previous talks because I could understand the resource acquisition is initialization. So we often found that we had code that looked a lot like this, and this is just the end of the function. We had a bunch of labels, and then of course throughout the function there's a bunch of go-tos, long before this that would jump and do the correct cleanup. This is an actual quote from the popen function, which opens a child process and returns a pipe to it. So, this is not something that's good if you want good, clean, maintainable code. This example is not from the C runtime. This is from an MSDN example, and I've used it in some other talks. But we had a lot of code that looked like this. It just wasn't quite as tight and compact. Like it was over the course of a 1,500-line function, we would gradually get further and further and further out to the right. And, then later we'd have to come back and do all the cleanup. So ideally what we wanted was something like unique putter. Unfortunately, we couldn't just use unique putter, and there's two reasons for that. Initially, it was because of layering. So the C++ standard library sits on top of the C standard library. And so just as a matter of practical code organization, we try not to have lower level things depending on higher level library facilities. This is, I think we're probably one of the only libraries where that is the case, that you would run into this issue. The other issue, though, that we ran into is that we needed to be able to get at the internal pointer. So we have a lot of, since we can't use exceptions, we have a lot of C APIs. Like I've made one up here, a get buffer that takes in a pointer to a char star, and it will return you the char star pointer to that buffer and return a status code of saying, yes, it succeeded, or no, it didn't succeed. In order to do that, we have to basically call the get buffer function with, the address of a char star. You can ignore that shouldn't be there. But if we change the buffer to be a unique putter, then that's of the wrong type, and so this won't compile. So we needed to get access to the stored pointer. The smart pointers that are part of the ATL library and the WRL library for use with COM or WinRT code provide functions named getAddressOf and release and getAddressOf. And this is because in COM you often have this pattern as well, because COM does not use exceptions. So we needed something similar to that. And so basically we just ended up writing our own unique putter. It was based on the STL unique putter plus a few extra functions that we needed. I think we didn't implement the whole API service because we didn't really need custom deleters. And we switched to using this for most of our internal memory management. I'd say probably on the order of 95% of the places that used to do manual resource management now do it automatically. There were some things that did not lend themselves well to this. We have some globally managed resources where we have to control during shutdown the specific time when we actually do the release. And then we have some thread local storage where we have to more tightly control the destruction. So the other thing we wanted to do is we wanted to make use of malloc within the CRT safer. So like I said, we can't use operator new, so we used malloc. And we had a lot of unsafe calls that look something like this, where we call malloc and then we call it with n objects times the size of whatever thing we're allocating, and then we cast it to that thing. So there's two problems that there are with this pattern. The first is that we name the type twice, which is fundamentally unsafe because there's a chance that you go and you name different types there, or maybe you use a type def in one place and not in the other place, and so then that type def changes and now you're allocating the wrong amount of memory. The second problem is that we really want something more like make unique behavior, where we allocate and we get back a smart pointer instead of having to allocate and then explicitly provide it to a smart pointer, otherwise it's going to leak. We want it to be safe by default. And so we did the most modern C++ thing we could think of. We wrote some macros. And I have to say, so why did we not use templates for these? So we did not use templates because in debug builds, we actually have different versions of these macros that track the file name and line number from which we did the allocation. And so if you use a template, that doesn't work with this anymore. And so we wanted a very straightforward conversion from the old malloc macro that we had to this new macro that took the type. And so we ended up just using macros. Could we have used a function template within here? Yes, we could have, but that was, again, we weren't writing perfect code. We were just trying to gradually improve it. So we ended up creating a total of, we only needed 3 little RAI containers to handle all of the resource management in the runtime libraries that we converted. So we needed the heap putter that we looked at before. We needed another one that was special for malloc A, which allocates memory on the stack. And then we needed a unique handle to use with things like file stars or Windows handles of various types. But those 3 were it, and they were maybe 70 lines of code each. So really, we wrote very little code, and most of this was stolen from other libraries that we have at Microsoft. And we were able to get 95% of our resource management to be automatically managed. So we ran into one big issue. Is anybody here familiar with the try finally construct on Windows? A couple people. So a brief introduction. So on Windows, there's 2 layers of exception handling. So the base layer is actually a facility provided by the operating system called structured exceptions. And structured exceptions are a general way of providing the ability to unwind the stack, due to something abnormal like an exception. The OS uses it for things like access violations. So the Windows equivalent of a segmentation fault is an access violation. So if you have a memory error like that, or you have a divide by 0 error, or some kinds of floating point errors, the operating system will let your application know about that by raising a structured exception. And when a structured exception gets raised, basically the operating system unwinds through the stack looking for handlers. C++ exceptions in the Visual C++ implementation are built on top of that. So a C++ exception is just a special kind of structured exception. Every structured exception has a status code, and we use a special well-known status code for the C++ exceptions. So when you write a try-catch in C++, what the compiler actually does internally is it converts that catch into the equivalent structured exception thing that it needs to do, and it just checks for that one particular code. And if it's not that code, it lets the unwinder continue unwinding the stack looking for something that does match. But you can also handle structured exceptions in general. And you do that using these special try __try __finally blocks. There's also an __ except, which you use if you want to actually handle the structured exception. But the way that we generally use it in the C runtime is anytime that we acquire a lock, we want to make sure that when we return from that function, even if we return abnormally, like let's say we call, for example, here we call malloc. Let's say malloc, causes a memory error because you've corrupted the heap somewhere in the process, and the structured exception starts unwinding. We want to make sure that if you are catching that structured exception, that we release that lock just in case you try to call back into the runtime library. We don't want to cause deadlocks. We don't generally support, if you have a an access violation, a memory error that causes an unwind. We don't generally support, calling back into the runtime library, but the intent is that if you have some critical cleanup, you'll be able to attempt to do that, or if you have some quick logging that you're going to do, and then you're going to bail out, or you have some custom termination logic you want to run, that any of that can run, and we want to minimize the chance of deadlock. And so we have a lot of code that looks like this. So we acquire the lock, and we enter the try block. And then in a finally block associated with the try, we call unlock on the same lock. Then within the try block, maybe we'll allocate some memory, and then we'll do something with it, and then we'll call free. So there's 3 problems with this code that we'd like to try and solve. So the first problem is the obvious one, and that is that we're not using RAII here. We call malloc, and then we separately call free. We'd really like to use RAII, so we'd like to use that unique pointer type that we had before. The problem that we run into here is that in the Visual C++ implementation, you can't mix and match C++ exception handling and structured exception handling. So here we actually have both. We have this buffer type with a C++ destructor, which is fundamentally related to C++ exception handling, because it needs to run when the exception unwinds. But we also have a try finally block in this function. So we can't have both of those in the same function. So this simple transformation is not allowed. We have a second problem here, and that is that we have this weird pattern where we define the result variable outside, we assign to it within the try block, and then we return the result. And we do this pattern, like what we'd ideally like to do, is like to just return directly from the try block, get rid of that extra variable, now the code is cleaner. Problem is, returning from within a try block is expensive, computationally expensive. It's basically as expensive as unwinding the stack from an exception. And the third problem that we have here is the try finally block itself. We have to explicitly call this unlock, which is fundamentally another RAII, another place that we should be using something like RAII. And so what we'd like to do is we'd like to have a unique lock type. Now, if we could do this, this would solve all of the problems that we just discussed. But there's one little problem, and that is that when the stack unwinds due to a structured exception that's not a C++ exception, so the access violation example from before, destructors do not get run. So basically, this would not do what we had intended for it to do. There is a mode in the compiler that lets you run destructors, but it's not recommended for use. It's a great way to get security vulnerabilities in your program. I can provide more info on that later after the talk, if you'd like, with lots of links to blog articles and things. So still, though, we want to have code that looks something like this. So what we ended up doing is we wrote a little wrapper, and we used lambdas. So lambdas are great because they allow you to package up a body of code and move it somewhere else and execute it in a totally different context. And so that's what we did here. So we wrote this helper function called CRT lock and call. And what it does is it takes a lock, takes one of our internal lock IDs, and it takes a lambda expression. And inside that lambda expression, we go and use all the C++ stuff that we want. And the way that it's implemented is what it does is it decides, okay, what's the type of the result of calling this function? And that'll be our result. It acquires the lock, it releases the lock in the finally block, and it'll return the result at the end. And inside of the try block is where we end up calling that lambda expression. So basically, we've taken up all of that C++ code that uses C++ exception handling and RAII types, packaged them up into a lambda. We've passed that lambda into this function, and this function will call it from the context that we want it to be called from. There is some slight runtime overhead for this. The compiler is not able to inline certain interactions between functions that use structured exception handling and functions that use C++ exception handling. But in general, when we're acquiring these locks, we're not in high-performance code. This is not, like memcopy or something like that, where we need to be really fast. The only other complexity that we have in the actual implementation is we have to have a specialization for a void return type, which we have a few of. and that version is just simpler. So I bring this up because this is actually very similar to another pattern that you can use in your own code that I've talked about in a couple other talks, and there's links to at the end. And that is when you have an old code base and you're trying to start introducing the use of exceptions. Like let's say you're in a code base that doesn't use exceptions, and you've got a function and you really want to use std vector inside of it. Well, you can't start using std vector there, willy-nilly, because I don't know if that translates. Anyway, willy-nilly. Just there we go. So you can't just start using it because some of its operations may throw bad alloc or may throw other exceptions, depending on what you're doing with it. And so what you can actually do is you can use that same pattern where you wrap up the code that you're actually that may use exceptions. So in here you could have std vector of int into a lambda, and you pass it into a translation function that will translate the exceptions into some kind of status code that you want to return, or if you want to just terminate the process or whatever you want to do. And then inside of that function, you just open up a try block and you make the call to the function, to the lambda. All right. This is one of my favorite things, but it's very simple, so it'll be quick. So the const keyword is one of the best things that C++ has. And I think everyone here is familiar with const correctness, I would guess. Almost everyone here is familiar with const correctness. So the idea of const correctness is that if you have a function that has a pointer or reference type parameter, and the function is not going to modify the thing that's pointed to or referred to by that parameter, then the pointer or reference should be const qualified. So basically you're telling your caller, I'm not going to modify this thing. My argument is that const correctness should be considered the bare minimum. And that, the common approach to const is that, well, you only make APIs const if you have to, and then you only add const wherever else you have to because you've made your APIs const correct. And I argue this is backwards. We should be making everything that we can const, and we should refactor code where required if we can do so in such a way that enables us to make more things const. So I have an example here of a little function. It's called read elements. This is very similar to what the fread function does, but this is much simplified. And so it takes in a buffer and an element size and an element count, and it's going to go and multiply those together and then read that many bytes by calling this read byte function. So it's going to go and compute the size of the buffer, the number of bytes that it's going to have to read. It's going to go and get pointers, byte-sized pointers, into the buffer. And then it's going to iterate over the buffer and read bytes into it until that fails or until it completes. So the question here is, how many places can we add const? I have 10 minutes left. Okay. How many places here can we add const that we don't have it right now? Well, we don't have it in very many places, so. Well, first off, all of the parameters can be const. We don't modify them in the function, and by making them const, then when we get to the end of the function, we know, well, we haven't done anything that's going to have modified those, so we're kind of safe there. We can make the buffer size const. We don't modify that. We can make these two pointer variables const. Note that we're not changing what's pointed to, we're just changing the pointer itself. We're not going to make first point somewhere else. And when we do this, the only thing that we're left that changes in this function is the iterator itself. And you can't make an induction variable const because induction variables, by definition, change. There are cases where you may have a bit more complex initialization. So this is, a common pattern where you test a Boolean and, check and, if it's true, you do one thing. If it's false, you do a different thing. And you can easily combine those two using, the ternary operator. If you want to confuse your code reviewers, you can also use lambda expressions here. So, for example, here, we've just moved the initialization code into a lambda. And instead of assigning the lambda to something, we just call it in line and use its value to initialize the variable. I think I've only done this once, and I confused several of my code reviewers as to why I did it, and so I haven't done it since. Yes? Why should the pointer, why should this pointer not be constant? They can't, so those cannot be they cannot be pointers to const because we're going to modify the things pointed to, right? So we're going to iterate over this, array, and we're going to read bytes into the array. So while we don't read directly from, I guess the last one could be, but while we don't read directly into the first one, we use it to initialize the iterator. All right, so there's only a few things that don't need to be const. Data members don't need to be const. If you have a function that returns by value, you should return int, not const int. Class type local variables that you may want to move from should not be const because it'll inhibit move semantics. You won't be able to move from it. And class type local variables that you may return from a function should also not be const for the same reason, because they will be moved from if you have a return statement. We also tried very hard to reduce use of the preprocessor in the code base. So my favorite example of this is we have this function named output. And output is the actual implementation of all the printf functions. So I believe there's 195 different printf functions. We have sprintf and fprintf and just normal printf, and we have a few Microsoft extensions like cprintf, and then there's _s secure versions of all of these printf functions. We also have a Microsoft extension that allows you to use positional format specifiers like in .NET. But anyway, way back in the beginning, when this thing was first implemented, we just had one, and we just had the printf functions which wrote char elements out to a stream. And then, Unicode came along, and we needed to add support for wchar-t. And so the way we did that was with the good old C-style generic programming approach. We took the file, we compiled it twice, once with Unicode defined, once with Unicode not defined, and then we if-def'd throughout the code. And so this is just the declaration, but there were also a whole bunch of if-defs throughout the definition of the function as well. Then later, someone came along and they said, well, it would be really great if we could add support for positional parameters. And so we did that too, and we added 2 more versions of the functions, and then throughout this function, there were a whole bunch more if-defs. Remember, this is just the declaration. By the time I got to it 3.5 years ago, this is just the declaration. And actually, I lied. This is only 2/3 of the declaration. This is 12 of the functions. There are 6 more. This was a 2,700-line file. This one function spans 1,500 lines, and there were 223 conditionally compiled blocks of code. So from a maintainability standpoint, this is just terrifying. And actually, it was terrifying. In Visual Studio 2013, we made an effort to go implement as much of C99 standard library as we could. So we added a bunch of new functions. And one of the things that we were missing was missing support for some of the new length modifiers that were added in C99. So for example, you can say %zu to print out a size t object, or an object of type size t. The z is new in C99. And we looked at this to try and add support for the z length modifier, and we're not confident that we could make such a change without completely breaking everything. So in short, this code gradually became quite unmaintainable. And so what we ended up doing is we, if we go back to the simpler example where we had just the 2, we converted that into a template that was generalized over the character type. And then we just defined the individual functions as calling that common function with the right kind of arguments to get the right behavior. And then for any places in the implementation where we had to have different behavior for the 2 character types, we just had overloads of other functions that did that for us. Now it was a bit more complicated than that, but in general we used very simple templates, mostly very simple templates, to accomplish that. So we ended up with 3 different what we called output adapters, which were each for the different ways to output data. So one of them wrote the data directly to the console, one of them wrote data to a file star, one of them wrote data to a string. We then had 3 different custom base classes that provided some customizable behavior to enable support for the _s, the secure versions of the functions, and then the versions that supported positional parameters. And then we had this final type output processor that just combines everything together. And all of this is in the source code that ships with Visual Studio if you're interested in learning more. I'm going to have to skip through a little bit of things. So this section, I wanted to talk a little bit about some of the changes that we made for being able to ensure that we could maintain binary compatibility. So everything that we've talked about so far was more general, like we were just trying to improve the quality of the code so that when we had to make changes in the future, we could look at the changes and really understand how they interacted with all the other parts of the system. Right? If you have really clean code, then it's really easy. It's much easier, to look at a code review and understand how it impacts other parts of the system. Whereas if you've got a 1,500 line long function, even if you're only changing one line, like, how do you know all of the different ways that you get to that line inside of the function? So one of the biggest things that we did here was we encapsulated implementation details. So our C standard library headers used to leak a whole bunch of implementation details through the headers. And one of the biggest examples of this is file. So we actually defined the file structure inside of the header with all of its data members. There were reasons for this. It was the easiest way to do it. People started depending on pieces of this in some cases. But this is fundamentally a problem because there's none of this is documented. We don't document what the behavior of any of the members are. It's supposed to be an opaque type. The only way you're supposed to operate on a file star is by passing it to like fread or fclose or other functions that actually are defined as working on the file. And the reason that we ran into a problem here is that in the future we might need to change the definition of this file structure. And in fact, that had already happened some 20 years ago when we added support for multi-threading to the runtime library. And internally, we actually use a file X structure that has an extra Windows critical section that protects the stream to allow it to be accessed from multiple threads. So what we ended up doing during the refactoring is we basically totally encapsulated all the implementation details. We could not make this just a forward declaration because of some weird C rules. Ideally, we would have done that. But instead, we made it a type with just a placeholder to hide all those implementation details. Well, with that, we then ran into a problem that the size was actually important for some of the things that were in the header. Notably, stood in, stood out, and stood err, the standard streams, were defined as calls to this function that returned a pointer to an array of file objects. And so the first element, or the initial element, was stood in, the first element was stood out, and the second element was stood err. So this relies on us not changing the size of the file. But we just changed the size of the file because now it's just got this placeholder thing. It's not the actual file object. And so we ended up having to change that function. And so now it takes an ID of the stream that you want, and so now we don't leak that size information. This was actually this has been a very painful change for us and for many of our customers. We know that this especially broke backward compatibility with a lot of static libraries that were built with old versions of the headers. We also worked to eliminate C++ and data exports. So C++ exports are problematic, as I said at the beginning, because the C++ ABI is not standard. And then the data exports are problematic because when we export like a global variable, well, we're exporting the fact that such a global variable actually exists and has a particular meaning, and we can't change that. And so we ended up switching those to be function exports. I'm going to skip that section. We made some conformance. I guess this was one of the other biggest things that we did. So we knew we had this big bucket of conformance fixes that we needed to make. We knew there were all these C99 features that we needed to implement. And so we went through and we actually audited our C standard library implementation to try and identify as many places that we were non-conforming as we could and go and fix all of those before we shipped. And so that would reduce the likelihood that we would need to go through heroic efforts to make bug fixes without breaking backward compatibility. We did a lot of that work in Visual Studio 2013 with the new math library functions, but then in the Universal CRT, when we did the big refactoring, that was when we were able to do basically all of the other stuff. And if you look at the breaking changes documentation for the runtime libraries, you can see there what all of those changes were. We exhaustively list them. with that, I have run out of time. So we will make the slides available, and the other ones are kind of self-explanatory. But I have a few blog articles here that are, on this Universal CRT project. This is most of the information that I presented here is either from those articles or from the source code. So with that, someone liked this before. I like it too.